Hello everyone. So now I'm going to give an video on an important topic in structure analysis, that is slope deflection method. So analysis of a structure by slope deflection method. Okay. So before going into the problems, let me introduce some of the facts related to the slope deflection method. Okay. So this method was first introduced by the Professor G. A. Manning in 1915. Okay. So the analysis of continuous beam can be carried out by adopting the rotation and deflection of each support, and hence it is referred as slope deflection method. Okay. So this method can be effectively applied to analyze both the statically indeterminate beams as well as the portal frames. Okay. So in this slope deflection method, here the joints are considered to be rigid, okay, which means that the joints rotate as a whole and the angle between the tangents to the elastic curve meeting at the joint will not change due to deformation. Okay. This is one of the major assumptions that is being carried out while analyzing by using this method. Okay. So the rotation of the joints are considered as unknowns. Okay. A series of simultaneous equations are formed, each expressing the relationship between the moments acting at the ends of the members or written in terms of slope and deflections. Okay. So this equation of slope and deflections along with equilibrium conditions, so this provides the values of the unknown rotations of the joints. By knowing these rotations, the end moments are calculated using the slope deflection method. So the moment, that is the end moment calculated, from that we can able to determine its bending moment diagrams. Okay. So the moment MA in a typical member AB, for example ABA, is made up of 4 parts. Okay. So MFAB and MFBA, so these are called as fixed end moments. Okay, whereas the ends A and B, we are considering it as fixed end. Okay, then we are calculating this as fixed end moments. Okay, so due to the transverse loading on the member, okay, where A and B are restrained from rotation or restrained, that is restricted from the vertical displacement. Okay, the second part is the moments due to rotation theta A of the support A only. Okay, then the moment due to rotation theta B of the support B only. Then the fourth part is the moments due to deflections, that is del A at A and del B at B, that is the both of the supports. Okay, so these are the 4 major parts that is involved in a slope deflection equation. Okay, next coming to the sign convention. Here, while analyzing the members or structures by this method, we are going to follow a fixed sign convention. Okay, so while coming to the moment, the clockwise moments are always considered as positive and the anti-clockwise moments are always considered as negative. Okay. Then coming to the rotations, so similar as moment, the clockwise rotations are always considered as positive and the anti-clockwise rotation is always considered as a negative. Okay. Then coming to the settlement or sinking. So in problems you can able to say that in question they may give like the support B sinks by so and so mm, support C sinks by so much so mm. Like this they maybe provide the problems. Okay. So in that kind of problems we can take settlement as negative if the right side support is below the left side support. Okay. Similarly, if the settlement del is to be considered as positive, means that is in the case of the left side support should be below when compared to the right side support. Okay, so we can see here we consider this span. Okay, span AB AC with the support intermediate support B. Okay, here the support B is settling by a value of del. Okay, in span AB, if you consider span AB, here we can see the support B layer. So this support B is below when compared to the support A. Okay, so here del is considered as an, in AB we consider del as negative. While taking support BC, here the left side support is below when compared to the right side support. So here we can take it as del as positive. Okay, so this is how we can take. Then coming to the slope deflection equations, we have already been discussed that the slope deflection equation consists of four different parts. Therefore, the first one is the friction moments. Next one is the moment due to rotation at A. Then moment due to rotation at B. Then moment due to the differential transverse displacement. That is the moment due to the displacement or settlement. Okay. So for a span AB, so this is how these two are the slope deflection equation. That is M of AB, that is friction moments. Then rotation due to support A, that is 4 EI theta A by L. Then uh, rotation due to the support B, so 2 EI theta B by L. Then moment due to the displacement or the settlement, 6 EI del by L square. Similarly, for considering moment at BA, so M of BA plus 2 EI theta A by L plus 4 EI theta B by L plus 6 EI del by L square. So here we can take it as 2 EI by L as common outside. So the equation can be changed as like this. Okay, so this is the basic equation we'll be using in the problems. Okay, this equation is called slope deflection equation. Here we can see the rotations theta A, theta B and del. These three are the unknown values, unknown variables. So we are forming this equation. If we are solving means we can able to get these values. After getting these values, if we apply a substitute here, you can able to get the moments. Okay. So the another important term or factor or concept, so to be known for analyzing a slope deflection equation is the joint equilibrium condition. Okay, so let me make it as simple. So we know the at a joint the sum of moments will be equal to 0. This is the very first important condition. Okay, at a joint the sum of all the moments is equal to 0. Okay, then coming to the second joint equilibrium condition. So if a structure has a lateral displacement, means if the structure has a lateral displacement, okay, then the horizontal equilibrium conditions are also should be applied. That is summation h is equal to 0 should be applied. Okay, then the sum of all the moments of a member meeting at any joint must be equal to 0. Okay, then another important term is the shear condition. Okay, so this occurs only in frame kind of problems. Okay, while solving the portal frames with the lateral displacement, we'll be having another additional condition that is called the shear condition. Okay, that is in shear condition the sum of various shears in the members so must be equal to the external shear. So this is one of the major important condition. Okay. Then coming to the procedure of slope deflection method, so the very first step is we need to find the fixed in moments. Okay, so the fixed in moments at the end of each span. Okay, for example, if you are having span A, B, C, D, so first we need to consider span AB. We need to treat the support A and B as fixed support. Then we need to find the friction moment. Similarly, for all the spans, we need to consider the values. Okay. Then after calculating the friction moments, we need to express the n moments in terms of friction moments and the joint rotation. That is, we need to form the slope deflection equations. Okay. After forming the slope deflection equation, we need to write down the joint equilibrium conditions. So we need to apply this joint equilibrium conditions in the slope deflection equations. Then while solving these slope deflection equations, we can able to evaluate or compute the final end moments. Okay. After computing the end moments, we can draw the bending moment diagram. Then we can determine the reactions and we can draw the shear force diagram. Okay. So the following some of the cases, this is standard cases. Okay, standard cases based on the loading conditions. We have standard formulas. Okay, for finding these fixed end moments. Okay, just I'm giving them major loads. Okay, we may not able to go through all the conditions. So for first one, if we have a load or point load or concentrated load at the mid span, the formula is minus WL by 8 and WL by 8. Okay, so next, if the concentrated load is acting eccentrically, okay, then the formula changes. Similarly, there are different kind of cases. Okay, if in this case we have 2-point loads. Okay, here we have an uniform distributed load. So we have formula of minus WL square by 12 and plus WL square by 12. Okay, so we have this is also one kind of uniform distributed loading pattern. So this is the formula to determine the friction moments for uniformly varying load. Okay, these are the formulas for uniformly varying loads. Okay, so we can just go through. This is the standard formulas. Okay, so now let us come on to the move on to the problems. So first kind of problem is the analysis of a continuous beam by slope deflection method. Okay, so for the first problem, we have continuous beam span of ABC. So there are two spans AB and BC. In span AB, we will be having a concentrated load, a point load of 90 kN acting eccentrically, and the span BC carrying uniformly distributed load of 80 kN per meter with intensity. Okay. So coming to the first step, we need to find the friction moments. So first we need to take the span AB. So in span AB, we are having so point order, yeah. So the formula is minus WAB square by L square and WA square B by L square. So by substituting, we can able to get the value. These are standard formulas which have been seen in the previous slides. Okay. Then move on to the span BC. We have uniformly distributed load with an intensity of 80 kN per meter. So we have formulas. We are just substituting these values. Then we are obtaining the friction moments. Then move on to the second step. Once we determine the friction moments, we are formulating the slope deflection equations. Okay, so MAB we have the standard formula. Since there is no support sinking or deflection is occurring, so this del will be equal to 0. So in question they have not explicitly mentioned any sinking related terminology. So this term will be equal to 0. Okay, so in both spans we are substituting these values and we are getting the slope deflection equations. Okay, then after computing slope deflection equations, we are moving on to the next step, that is the joint equilibrium condition. We are writing the joint equilibrium conditions. Okay, so the first condition we are by moving from joint to joint. First we take the first joint, that is joint A. So in joint A it is a fixed end, right? So in fixed end there will be moment. So and there also another scenario that the slope at a fixed end will be equal to 0. Slope at fixed end will always be equal to 0. Similarly, joint C. So joint C is a fixed end. Sorry. So joint C is a simply supported end. Okay, so in simply supported end, we'll be having the slope values. In simply supported ends, we don't have the moment values. So on joint B, so we already know that. So sum of moments at a joints will be equal to 0. So a joint B, the sum of moments is equal. These are three major joint equilibrium conditions. Okay. Now we are applying these joint equilibrium conditions with the previous step 1 step 2 equations. So we are applying this and we'll be obtaining two equations. Okay, there will be two equations. So in here two equations we have two unknowns, that is theta b and theta c. Here theta b and theta c, there are two unknowns and two equations. So we can able to solve these two equations. While solving these two equations, we'll be getting the value of the two unknowns, that is value of theta b and theta c. Okay, now we substitute the value of theta b and theta c in the step 2 equations. So we'll be getting the final values of moments. Okay, then the last step, that is last step, another step is the bending moment diagram. Okay, we already calculated the moments, that is the moments at the supports. Okay, then for bending moment diagram we need to find the maximum bending moment value. We have formula for span AB, we have a point load, so the formula is WAB by L, and for UDL we have formula is WL square by 8. These are the maximum bending moment values. Okay, so we are just based on the moment values we are drawing the bending moment diagram. Okay, then coming to the shear force diagram, we are taking span by span. So we are taking moment at any of the joints. Okay, then we are finding the reactions. So based on the reactions we are drawing the shear force diagram. Okay, so this and all we have studied, or we will be able to know in the previous strength of materials related subjects. Okay, next we move on to the next problem. It's also a continuous beam. Okay, so a continuous beam ABCD, it's a 12-meter long. So if it is fixed at ND and is loaded as shown in figure, that is, it's loaded the span AB. We have a point load or concentrated load 8 kilonewton acting at the mid span, and in a span BC we are having uniformly varying load with its maximum intensity at the mid span, and we are having in span CD an uniformly distributed load with intensity of 1.5 kilonewton per meter. Okay, so another important term they have given us, that is the end A, the support A yields or it rotates by 1 by 250 radians in clockwise direction. We already know that in fixed support there will be slope will be equal to 0. That is the basic condition. But here the additionally the end A yields by, that is we have theta value, theta A yields by 1 by 250 radians, 1 by 250 radians in the clockwise direction. Similarly, the end B sinks by 30 mm in the downward direction. So then end C sinks by 20 mm in the downward direction. So they have given the values of I, that is the sorry. So we have the moment of inertia I, then the Young's modulus. Okay. Then we come into the solution. The first step similar that is we will be calculating the friction moments. Then the step 2 we are computing the slope deflection equations. Well, calculate slope deflection equations. In question they have given us while taking the span AB. So we have a sinking condition. Support B sinks by 30 mm. So now we have the value of del here. In previous problem they have not mentioned any sinkings, so we have taken del as 0. But here, so we have del as 30 mm. We need to apply these values. Okay. So we will be arriving different equations. So apply the del values, we having two equations. Then while considering the span BC, so in span BC, right, we can able to see both the suppose B and C are sinking. So we need to find the net displacement. Okay, so the net sinking value. So net sinking value, then we are adding it. Okay, then we are applying it in span MBC. Okay, then in MCB similarly we are arriving the values. So we have arrived the slope deflection equations. Then coming to the joint equilibrium condition, at joint A we have value theta A is equal to 1 by 250 radians, that is the given value. In joint B we have the sum of, we know that the sum of moments at a joint will be equal to 0. Similarly joint C, sum of moments at joint C is equal to 0, and at joint D, so we know, yeah, so in joint D is a fixed support. In fixed support we know theta D is equal to 0. So now we are going to apply these values in the slope deflection equations. So then we are arriving two equations. Okay, so two equations, theta B and theta C. Okay, so we are having theta B and theta C with two variables or two unknowns with two equations. By solving these two equations, we can able to get the values of theta C and theta B. Then now next step is we are taking this theta values and substituting in the step 2 equations, that is the slope deflection equations. Then we can able to arrive the values of the end moments. Okay, after once you determine the end moments, you can able to calculate the maximum bending moment values based on the loading conditions. Then we are determining the we are computing the bending moment diagrams with the values of the maximum moments and the values which have been calculated from the deflection equations, that is the support moments. Okay, next, so we are going to analyze a frame or rigid frame or portal frame without sway. Okay, so sway means and all I will be discussing later. So just we can able to remember that sway is nothing but lateral displacement or horizontal displacement. Okay, so in this problem, so we have a portal frame. Okay, with a point load or concentrated load at the span BC acting at the midspan. So this kind of problem, or well, so this kind of solving a problem without sway, rigid frame problem is more or less similar like as we are solving in the continuous beam problems. Okay, so the first step is, as usual, we are finding the fixed in moments. Okay, so here we know in span AB and span CD we don't have any loading conditions, so the fixed moment will be equal to 0. So in only in span BC we have load. So in span by sorry for in span BC only we are able to retrieve the fixed moment values. Okay, then in step 2 we have slope deflection equations. So here we have there is no, because it's a without sway kind of problem, there is no horizontal loading, so there will be in question also they are not mentioned any sinking, support sinking and all, so del will be equal to 0. Here we know, yeah, so theta A we can directly take theta A is equal to 0 because A is a fixed end. Similarly D is a fixed end. While considering span CD we can take theta D is equal to 0. Okay. So we are applying all these conditions and we are arriving the values or the slope deflection equations. We are arriving the slope deflection equations. Okay, then coming to step 3, that is the joint equilibrium conditions. So we know that joint A, the theta A, that is joint A is a fixed support. So the in fixed support the slope will be equal to 0. In a joint B we have it is an intermediate end area, so the sum of moments at a joint will be equal to 0. Similarly joint C also, the sum of moments at the joint will be equal to 0, and joint D we know that it is also a fixed support, so the slope will be equal to 0. So we are applying these conditions, we will be arriving two equations, so with two unknowns theta B and theta C. While solving these two equations, we can able to get the values of the two unknowns, that is theta b and theta c. Okay, so the next step is we are going to substitute this theta b and theta c in the Slope deflection equations, and we will be arriving the final end moments. Okay, then coming to the bending moment diagram, we will be calculating, we will be uh, computing the maximum bending moment values. Then we are drawing the bending moment diagrams. Once bending moment diagrams are being computed, we can able to take the individual spans, taking the moments at any one of the end, then we can able to get the reactions, and then the shear force diagram we will get. Okay, this is the shear force diagram. Next, so next is another important concept, that is the analysis of rigid frames or considering the sway. So let me first explain what is sway. So sway is nothing but the lateral movement of the frame. So lateral movement or the horizontal movement. Okay, so if the frame consists of, or if the frame consists of a loading system or the geometry, if the both the loading system and the geometry is not symmetric, so the frame will be having the side sway. Okay, so we will be discussing the main, what are the main causes of sway in upcoming topics. Okay, so next is the important one of the main question, that is how do you account for sway in slope deflection methods for protectums. Okay, so we know that because of sway we'll be having rotations in the vertical members. Okay, so this causes a movement in the vertical members. If the vertical members starts to rotate, so there's a movement is will be automatically induced. So in order to account for this movement, apart from the basic equilibrium condition, yeah, one more equation that is called as shear equation is considered. Okay, so the shear equation is formed by connecting the joint moments. Okay, we will be considering the shear equation, then we will be analyzing the problems. So let us discuss what are the causes of sway. Okay, so the first main reason is due to the unsymmetrical loading or the eccentric loading. Okay, if the frame is possessing any unsymmetric loading, excess loading, eccentric loading, the frame will tend to sway. Next, it is unsymmetrical geometry. For example, if the span AB have 3 meter, if the span CD have 2 meter, okay, so we have unsymmetrical geometry. Okay, so the sway will occur. Then different end conditions. For example, if the joint A have fixed end and the joint D has a hinged end, so yeah, so this kind of similar, possibilities may occur. Okay, then varying sections. Okay, that is the cross sections of the different members, the sway will occur. Then if an horizontal load is applied on a frame, okay, if an horizontal load is applying on a frame, so this side sway will definitely occur. Okay, then the differential settlement of supports. For example, they may ask the support A sinks by 10 mm or support D sinks by 20 mm. Likewise, the differential support settlement of supports will causes the sway. Okay, so these causes may occur individually, or it may occur a combination of possibilities. Okay, so we know that a rigid frame. So a rigid frame is nothing but a structural frame in which all the columns or beams are rigidly connected without any hinged joints. Okay, such kind of frame we will be calling as a rigid frame. Okay. So this rigid connection, what we will be doing now? So this rigid connection will resist the movements induced at the joint and able to take the bending moment, shear and the axial. Okay, it's just one of the IQ purpose. Okay, then coming to the problems, you'll be seeing on problem. That is, we are going to analyze a portal frame with the loading condition below. So we are analyzing by slope deflection method. Okay, so here we can see. See, in questions they will not mention that it is a sway or it is a non-sway kind of problem. They will not mention. So based on the diagram or based on the given figure, we need to identify whether we need to solve this frame by using the concept of sway or by without using the concept of sway. Okay, here we can able to clearly see that the load is eccentrically acting, not acting at the midspan. In the previous portal frame, we've been seeing that the load is acting exactly at the midspan. So there is no possibilities of lateral displacement. But here the load is acting at the eccentric distance. That is 2.5 meter from the right, from the left, and 1.5 meter from the right. So it is evidently showing that it is a sway kind of problem. Okay. As usual, we can first we will be calculating the friction moments. Okay. So in step 1, there is no load or external loads acting at the span AB and CD. So the friction moments will be equal to 0, and only one load is acting at the span BC. So we are calculating the friction moments. Then coming to slope deflection equation, we know that eccentric loading is acting on the portal frame. It causes the frame to sway. Okay, so let us assume the span BC is moving horizontally with a distance del. Okay, then based on this we are formulating the slope deflection equations. Okay, then after calculating the slope deflection equations, we are writing the joint equilibrium condition. We know the joint A, we know that slope will be equal to 0, and joint B the sum of moments will be equal to 0, and in joint C sum of moments will be equal to 0, and in joint T we know that slope is equal to 0. So since it is sway kind of problem, additionally we need to include one more equation, that is the shear equation, because you see, let me we continue. Let me explain later why we are using this third equation. Okay, so in shear equation we are considering the shears. Okay, that is MAB plus MBA by LAB plus MCD plus MDC by LCD is equal to 0. It is the formula for formulating the shear equation. Just we are applying these three equations. Okay, so here we can able to see theta B, theta C and del. So these three are unknowns or variables. Okay, so in previous problems and all we can able to see only two unknowns. So for in order to identify the values of two unknowns, we need two equations. Then only we can able to solve these two equations and we will get the values. So similarly for analyzing for determining the values of three unknowns, we need three equations. Okay, so in joint B, this if we take this equation, if we take in this condition, we will be getting one equation. Next, if we take this condition, second the joint C condition, we will be arriving two equation. So but we need to have another equation, that is why we are using the shear equation. So by using shear equation we can able to get one more additional equation. So we will be able to get three equations, and these three equations are having three variables, so and it will be easy to solve. Okay, by using the joint C condition we are getting the second equation. Then next we are using the shear equation, so we are obtaining the third equation. So in three equations we have three unknowns, theta B, theta C and del. So here theta B, theta C and del. So we are solving this equation, we will be getting the values of theta B and the values of theta C and the values of del. Let's substitute all these three values in the slope deflection equations. We will be getting the values of the final end moments. Okay, so by obtaining n moments, we can able to draw the bending moment diagram. Then after obtaining the bending moment diagram, we will be determining the reactions. So then we can draw the shear force diagram. Okay, so that's all about the short video, short lecture regarding the analysis of slope deflection equation. So I'm just giving a short recap. So initially we have seen what are the basic introduction about the slope deflection equation, because how the slope deflection equations are arrived, what are the major parts in the slope deflection equation, the sign conventions, then the joint equilibrium conditions, then the procedure to solve a slope deflection equation. Then the first problem we have seen regarding the analysis of continuous beam. The next problem we have seen analysis of continuous beam with the settlement of the supports. Then we have seen the analysis of a portal frame without sway, and at last we have seen what is mean by sway and the analysis of a portal frame with sway problem. Okay, so thank you. Have a nice day.